We're going to look at growth rates of exponential functions. So if many, so an exponential function can be defined by its growth rate. So what we need to write, and this is dt, is that we have the rate of change is defined by the constant of proportionality, which we call k, or that's the rate, times our output y. So if we think about like we're timesing all the outputs by a constant rate. That's how our exponential changes over time. That's why our differential equation is written as dy dt. Okay, so let's go ahead and derive this, or we're going to integrate. So I'm going to write dy over dt equals k times y. I'm going to separate and integrate. I get 1 over y is equal to dy, and that is equal to k times dt. We'll go ahead and integrate both sides, giving me the ln of the absolute value of y. I have an extra equal sign right there. Okay, is equal to k times t. K is a constant. Okay, plus c. And then I'm going to raise both sides as the exponent with a base of e. And then I end up with the absolute value of y, which I'm going to write just as y, because what I remember is that the e to the c comes out as just c, so I'll put c1. C times e to the kt, and the plus and the minus from the absolute value gets absorbed into that c value as well. Okay, so if you notice that we end up with an exponential function, because we know that the rate of change of an exponential function is just k, so a rate times its output. So anytime you see a rate of dy over dt is equal to k times y, you know that you're going to end up with an exponential function as its solution. Okay, and a couple things to note is that the c is the initial value and k is the constant of proportionality, t is the time. All right, so honestly, a lot of these problems, they just are pre-calc problems with us recognizing that the pattern is that the rate of change pattern is exponential. Okay, so we have the rate of change of y is proportional. So when we say it's proportional to y, we know it's k times y. Okay, when t is equal to 0, y is equal to 2, and when t is equal to 2, y is equal to 4. So those are our 2 points. We can write them as 0, 2 and 2, 4. And this is t and y. Okay, so what is the value of y when t is equal to 3? So we really just need to write an exponential function. So we're going to go ahead and start with dy over dt is equal to k times y. We know that when we integrate, we end up with y is equal to c times e to the kt. So we need to find we have 2 points that our function passes through, and they are 0, 2 and 2, 4. I recognize that 2 is my c value because it is the initial value of my exponential function. So I can now write y is equal to 2 times e to the kt. And now I'm going to go ahead and substitute in 2, 4 to find my constant of proportionality. Okay, or proportionality constant. Okay, so we have 4 is equal to 2 times e to the k times 2. And then we need to divide. So I get 2 is equal to e to the 2k. You can ln both sides. I'm going to go ahead and snail. So I'm going to get the ln base e of 2 is equal to 2k divided by 2. So I have k is equal to 1/2 times the ln of 2. So my equation is 2 times e to the 1/2 times the ln of 2 times t. Okay. Next, we have to figure out when y is equal, what is y when t is equal to 3? So we're going to evaluate y of 3, which is 2 times e to the 1/2 ln 2 times 3. And when I substitute that all in, I get y of 3 is equal to 5.657. Okay, so when t is equal to 3, y is equal to 5.657. Okie doke. Let's do another. All right, so radioactive decay. The half-life of plutonium-239 is 24,100 years. Suppose that 100 grams of plutonium-239 was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? So again, this is the half-life of a material. So this is going to be decay, an exponential decay. So I can start off with my dy dt, sorry. Ooh, did I write that? Okay, is equal to k times y. And then we know that the solution is going to be y is equal to c times e to the kt in that form. And some information that I know is that we are starting, so our c is equal to 10 grams. And then I also know that the half-life is 24,100 years. So that means that when t is equal to 24,100 years, I will have 5 grams of plutonium-239. So that's going to be my point. My t and I put my y. Okay, so up next is to figure out what our proportionality constant is. So let's plug in our 24,100, 5 into our equation. So I get y is equal to 10 times e to the kt, and then we're going to plug in our point. So I get 5 is equal to 10 times e to the k times 24,100. Now divide. So I get 1/2 is equal to e to the 24,100 k. Yeah, that's enough zeros. You can ln both sides. I prefer to just snail. So we get the ln of 1/2 is equal to 24,100 times k. Divide. So I get k is equal to the ln of 1/2 over 24,100. So I end up with an equation that looks like y is equal to 10 times e to the 1, I could use some more space. Okay, to the 1 over, actually, I'm just going to write the ln of 1/2 over 24,100, and that's all times t. And then it says, how long will it take 10 grams to decay to 1 gram? So that's my y value. So I'm going to plug in 1 for y to figure out its coordinating time. the ln of 1/2 over 24,100 raised to the t power. All right, so we divide by 10 first. So that's 0.1 is equal to e to the ln of 1 over 2 over 24,100 times t. Then I prefer to snail, so I'm going to do that. So I get the ln of 0.1 is equal to the ln of 1 over 2 over 24,100 all times t. Okay, then I'm going to multiply both sides by 24,000. 24,100 times the ln of 0.1, and then divide both sides by the ln of 1/2. Okay, so I get t is equal to the ln of t is equal to 24,100 ln 0.1 over 1/2, which is equal to 80,058.467 years. So to reduce to 1 gram, it's going to take us 80,000 years, 80,058 years. It's going to take a long time. Okay, we're cutting in half and then half and then half again. Okay, so how about when we don't start with our C value? How do we do this again, y'all? So we have an experiment with fruit flies increasing according to the law of exponential growth. Okay, there were 100 fruit flies on the 7th day and 300 fruit flies on the 4th day. So how many were in the original population? That would be my C. So how many is in C? So I see that we are changing according to exponential growth. So k dy over dt is equal to k times y. And then I know then that my exponential growth equation would be y is equal to c times e to the kt. I want to find out my C value in the end. Let's write down our 2 points. So our 2 points would be 7, 100 and 4, 300. Oh, 2nd day. Wow. Okay. I think I said the 7th day too. So it'd be 2, 100 and 4, 300. All right. So I'm going to use my first point to plug into the equation. So 100 is equal to C times E to the KT, and the T is replaced with a 2. So I'm going to isolate C. So I get C is equal to 100 over E to the 2K. And then I need to solve, I'm going to use the other point and plug in again. So 300 is equal to C times E to the 4K. And I'm going to substitute my first equation into the second. Okay. So I get 300 is equal to 100 over e to the 2k times e to the 4k. And when you divide bases, you subtract exponents. So I end up with 4k minus the exponents of 4k minus 2k, which is 2k. So I get 300 is equal to 100 e to the 2k, divide by 100. So I have 3 is equal to e to the 2k. So in other words, our, okay, actually, let's just keep going. So we have to snail or ln both sides, and I get the ln of 3 is equal to 2k. Divide by 2, and I get my proportionality constant is the ln of 3 over 2. All right, so the last thing we need to do is to solve for our C value. So I'm going to use this calculation right here since I already know the calculation to solve for C. And so I just need to plug in a value for K. So I get C is equal to 100 over e to the 2 times the ln, let's say 1/2 times the ln of 3. I think that'll be easier. 1/2 times the ln of 3. So the 2's and the 1/2 cancel. So I just have 100 over the e to the ln 3, which is just 3. So I have C is equal to 33.3 bar. So there are 33 flies in the original population. Okay. All right, last one. Newton's law of cooling. Okay, so let Y represent the temperature in degrees Fahrenheit of the object in a room whose temperature is kept at a constant 60 degrees, and the object cools from 100 to 90 in 10 minutes. How much longer will it take the temperature of the object to decrease to 80 degrees? Okay. Newton's law of cooling is defined by d big T over dt equals K times capital T minus capital M, where M is the surrounding temperature and T is the temperature of the object. So we can go ahead and write that down. dt over d time is equal to K times the temperature minus surrounding temperature. Okay, it told us the surrounding temperature was 60 degrees. So I can go ahead and plug that in. dt over d little t is equal to K times big T minus 60. Okay, so in order to figure out what the equation for temperature is, we're going to have to integrate here because I didn't give you this formula. Okay, so we're going to go ahead and find our solution by integrating. I am going to divide the t minus 60 to the other side. And also multiply both sides by dt. So I end up with dt, d capital T over capital T minus 60 is equal to K times dt. Integrate. I get my u is equal to T minus 60. So du is equal to dt. Okay, so I get the ln of u, which would be T minus 60, is equal to kt plus C1. All right, we're going to raise e to both sides, or we're going to make e the base on both sides, giving us the absolute value of t minus 60 is equal to, remember, e to the C1 is just C, okay, times e to the kt, and we're going to absorb the absolute value signs in the C value. Okay, so I get t minus 60 is equal to C times e to the k little t. Add 60 to both sides, so I get C times e to the k times time plus 60. All right, this is my equation. So now I need to figure out what my k value and my C value are so I can evaluate. So we're going to solve for K and C. So we know the information is at 0 times 0, the object is 100 degrees. And then at time, at 10 minutes, the object is 90 degrees. Okay, so it looks like I have my C value, so I can go ahead and write my equation as, actually, that's not my C value. I have to be careful here because I have that plus 60. So what I need to do is plug in, I am going to plug in the values, okay? So I'm going to be like 0 is, 100 is equal to C times E to the K times 0 plus 60. And then remember, anything that is 0 is 1. So I now have 100 is equal to C plus 60. So C is equal to 40. So I can write my equation as T is equal to 40 E to the KT plus 60. Now let's go ahead and solve for K by using our 10 comma 90. So 10 comma 90. So 90 is equal to 40 E to the K times 10 plus 60. Subtract 60, giving us 30 is equal to 40 E to the 10K. Divide by 40 to get our exponential by itself, the base by itself. So I have 3/4 is equal to E to the 10K. I am going to snail. Man, what would I do without snail? ln of 3/4 is equal to 10K. Divide by 10. So I get the ln of 3/4 over 10 is equal to K. All right, so we're ready to set up an equation. Now these just take a while. So I have T is equal to 40 E to the 1 ln of 3/4 over 10 times T plus 60. Let's make that T nice. And 60. Okay, and then the last thing it wants us to do is figure out what the time is when the temperature is 80. So I'm going to plug in 80 for T. You get 40 E to the ln of 3/4 over 10 times T plus 60. Okay, so subtract 60, and I end up with 20 is equal to 40 E to the ln of 3/4 over 10 times T. Divide by 40. We're almost there. So 1/2 is equal to E to the ln of 3/4 over 10 times T, snail. Okay, and I get the ln of 1/2 is equal to the exponent, which is the ln of 3/4 over 10 times T. Okay, multiply both sides by 10. So I end up with 10 ln of 1/2 is equal to the ln of 3/4 times T. Divide by the ln of 3/4. So I get 10 ln of 1/2 over the ln of 3/4 is equal to T. And that is equal to, the time is 24.094 minutes. So it takes 14.094 minutes to cool from 90 degrees to 80 degrees, because it says how much longer will it take the temperature to decrease to 80 degrees. Okay, and that is that for this lesson. We have one more lesson in chapter